Right. Okay. Welcome back. It's a great pleasure to welcome Juan Garrahan from Nottingham University, who's going to talk about quantum trajectories and some interesting analogues between the statistics of quantum trajectories and thermodynamic properties and phase transitions.
Okay, thanks. Thanks for the invitation. And so it was actually Madeleine who asked me to come and give, an overview of things that we've been doing in Nottingham at the School of Physics and Astronomy. And this is work with my colleague Igor Lesanovsky, then Bea Olmos, who's a postdoc, James Hickey, Robert Turner, two of my PhD students, and Chena Bates, Sam Genway, two postdocs who have left, and from maths, and this is something that also involves interactions with maths. This includes both Madeleine and Yuka, who are here, and Merlin Farhosen, who was a student with Madeleine, now is a postdoc with me, and some people from outside Nottingham, Christian Flint and Adrian Budini. And I'll try to give the overview, telling you where I come from to this problem, and I don't know whether I comply with Madeleine's instructions, but that's my take. So I wanted to say what my general interests are. I do statistical physics, and I'm mostly interested in statistical physics of non-equilibrium, and there are many problems in that category in classical physics, classical many-body physics. One of them is glasses. It seems to be stretched, and I'll talk a little bit about that. And another one is tilings and random coverings. And these are interesting problems where interesting non-equilibrium physics emerges in many-body setups. These are complex systems in the physics sense. So a few years back, first talking to Igor Lesanovsky and then to other people like Madeleine and so on, I also became interested in applying some of these stat-mech ideas from classical physics into quantum non-equilibrium problems. And one of those things that I'm going to talk about here highlights what we're calling quantum soft matter, the possibility of getting collective behavior like the one that gets in classical soft matter in quantum many-body systems. So, kind of battle cry is that dynamics is more than statics. So very often, interacting many-body systems can display dynamical behavior that is more complex than what the static, say the stationary properties, the one-time properties would suggest. And that's sometimes different from the standard thinking in physics, in condensed matter physics. So dynamics is more than statics. And if dynamics is more than statics, one needs some statistical mechanics so as to extract aggregate collective global properties from some microscopic description, but the statistical mechanics of the trajectories, because the trajectories are the objects that produced in the dynamics rather than the configurations or states. And I give you an example from my other line of work, that of the glass transition problem, classical glass transition problem. And most of what we know in physics about non-equilibrium comes from thinking about the glass transition problem. It's a complex unsolved problem in condensed matter science, and as people think about it and try to solve it and so on, produce ideas and techniques that then permeate across non-equilibrium. So, so the basic problem of glass is the following: you have a liquid, whatever it could be, and typically it's some silica meant or window glass. You cool it, it stays liquid, but it becomes very slow, very gooey, very sticky, and viscous, and eventually it falls out of equilibrium and forms a solid substance. That's what we call glass. That's been for 5,000 years or whatever. And glass is formed in a material that becomes dynamically arrested, that stops flowing, but in contrast to other solid materials, it doesn't get any structural order, at least no obvious structural order. There is an example. Of course, this was a bottle, was heated up, and then was cooled again, and it kind of illustrates what a glass is. A glass is a fluid that has stopped flowing. It's like time has stopped. It has become dynamically arrested. But if you look at a material of this kind, or the material that's about to become of this kind, structurally, it doesn't differ from a normal liquid. So if you take an X-ray, neutron scattering, whatever, if you look at the structure, you say, oh, this a normal liquid will flow like water, normal conditions or something like that. But then as an object, clearly it's not flowing, it's not moving, so it's dynamically arrested. And just to quote, this was made by my wife, who's an artist. She has a kiln for ceramics, so she can make these things. That's an example of, I think it's a nice illustration of what glass formation is about. So that's the problem of having structural arrest without a change, having dynamical arrest, so things not flowing, not moving anymore without any obvious change in structure. So now, if one thinks of the two possibilities to address this question, one can call thermodynamic and the other one dynamic. It's just to give you some overview of the kind of ideas that have been out there for many years. And the standard thermodynamic view, which is the basic one of the one approach uses in condensed matter problems, is that statics implies dynamics. And very often in this field, you see cartoons of some kind of energy or free energy landscape in terms of some configurational coordinate that's rugged. So then the idea there is that complex material like something that forms glass is complex both in its static thermodynamic properties, because there is a very complicated arrangement of minima and deeper valleys and blah blah blah. The distribution of these locally trapping states is very complicated, and that implies that the dynamics will be complicated. So statics implies dynamics, and that's a view that's very much tied into how we think of normal materials. A normal fluid flows because it's disordered. A crystal doesn't flow because it's ordered. So you look at the structure, there is a clear difference, there is a phase transition between the two, the dynamics will follow. When a problem like that of glass formation, generically, that doesn't seem to be the case. I told you that structure doesn't seem to change, but the dynamics changes massively. So dynamics does not seem to follow from statics. So that's if you want a dynamic view. And just to draw another cartoon, the thinking, instead of being that the arrangement of local minima is complex and so on, is that what's complicated is the connectivity of configuration space. So now think of a prototypical model for a fluid. That's a hard sphere, a liquid of hard spheres. So if you think of that, hard spheres as such that all configurations are possible and equally likely, if you want, if two of those hard spheres don't overlap. And then there are lots of impossible configurations where hard spheres overlap. So if you think of if you think of configuration space, it's like this Parque Güell in Barcelona. So it's everything's flat with very large columns of impossibility in configuration space. There is no complex arrangement of the allowed configurations. What's complicated is to go from one configuration to another. So the idea is that in this cartoon, that configuration space, there is no such distribution of allowed states, but if one wants to go from one configuration to another, the path can be very complicated. So to put it in between quotes, it's like saying it's not that there is a complex energy landscape, but there is some interesting or complex metric structure in configuration space. There's nothing special about any configuration being more likely than another, is that connecting two is complicated. And if one thinks of this idea, it's kind of very natural in any complex system. Going from A to B, of course, if there is something complicated like this, the path will be difficult to find as well, the optimal path, but there can be difficulty in finding the optimal path without the endpoints being anything special. Okay? So, this is the view we adopt. Dynamics is more than statics. The dynamics can be much more complex than static. By looking at these individual points, one wouldn't learn too much. One really has to look at the paths and therefore the trajectories. So now, let me give you a more concrete example. This is very clear in glass-forming systems with a phenomenon called dynamical heterogeneity. So here I'll show you simulation, and we've done lots of work on this. And this a simulation, I do it in a 2D fluid to be able to show you a movie. 3D one wouldn't be able to see too much. So this is a computer reasonably realistic liquid at conditions where the computer is about to form a glass, but it's still relaxing very, very slowly. And I will show you a movie. And probably cannot see, but there are, I don't know, several tens of thousands of particles here. There are little disks, and no matter how you try, if you try to find structure here, you would find anything. Wouldn't find anything. It is as disordered as any fluid would be. And I will run the movie, yeah, and the particles will get colored by how much they have moved over a period of time. The period of time that has elapsed in the movie. Okay. So again, this has no structure whatsoever beyond the tiny, tiny distance of individual particles. Now there's no structural correlations, of any kind. And now I will run the movie. And I will color the particles red. The more they have moved, yeah, over the period of time. And this is what happens. Yeah? Structure starts to emerge. Yeah? But this structure that you're seeing there, colored red and blue, and if I can stop it. Oh, sorry. So I run it again. So the structure that you see there, which starts to span many lengths of these particles, is dynamical information. What you're saying is the projection of a trajectory on the plane. Yeah. Any time slice wouldn't show any structure whatsoever. Yeah.
So there are nuclei that show up like red.
Yeah.
This means that in the vicinity of those points, things moving quite a lot.
Yeah.
And then in the other places that come and go means that particles move a little bit, but then the color is suppressed because the previous regions have more mobility, or
I think you're almost hitting everything on the nails on the head here. What happens is that yes, there are some particles that move more, and in the physics of this, which I won't go too much into, that helps neighboring particles to move more and neighboring particles to move more. So there are regions where there are particles which start moving, and then there are correlations with their neighbors in the dynamics, and the dynamics in that region is highly mobile. And then there are regions, the blue ones, where no particle is moving, there's no one to help anyone else, and those regions are immobile. Eventually, everything will go red, because this will run for long enough so that every particle will move, and this is still in the ergodic regime. But what one says is that over long but finite periods of time, there is an emergence of correlations in the dynamics. But again, if you have taken this movie, which I'm projecting on the plane, and taken still pictures, no still picture would show any structural correlation. Nothing special about the red and the blue or anything. This is something that only emerges on trajectories. Okay, and just to what I was just highlighting, this is a projection of a trajectory. One can undo the trajectory, and that's a little bit of the plane and time, and one sees these regions of where there is lots of motion or no motion, develop and propagate and so on, just to emphasize that this is an actual trajectory. And this is called the dynamical heterogeneity, the emergence of heterogeneity in space on the dynamics, where there is nothing on the thermodynamics or on the structure. So once again, dynamics is richer, and this is a clear illustration of that than what statics would suggest. So yeah.
I just wondering what the initial conditions were.
Oh, this is in equilibrium. So this is a stationary state.
Right.
So it's still in the liquid, but very, very, very slow before it's about to become a glass. And by the way, glass is just a convention. It's a liquid that's so slow that you cannot observe it relaxing on experimental timescales. So it's on the computer, a system which is very slow, but still ergodic. And it's an initial condition taken from its Boltzmann distribution in this case, because it's in contact with the thermal mass and so on, and then run along. So it's a reversible trajectory. If I show you the trajectory, you couldn't tell whether it's going forwards or back. Yeah? So it's in the reversible ergodic regime. Okay? So any slice is statistically equivalent to every other. And it's really how these slices follow each other. Okay? And that's where the correlations emerge. So all that's interesting is in the trajectories and not in the configurations. One needs statistical tools to analyze trajectories to an extent to the sophistication, if we can, that we do with configurations with standard statistical mechanics.
I have a clarification question.
Yep.
If I think about state space
Yep.
based thermodynamics, I can think of a parameter associated with the state, something like its viscosity, which is here locally varying. Right?
Which here would be so.
Is locally varying. Right? So I can observe in this particular parameter, this is a function of the state, that I could predict for the next time slice that there would be a lot of motion. In other words, it's not clear to me that this dynamical part isn't actually encoded in the state. If you just look at the correlation function.
We're almost going. Yep, it's an appropriate question. So I can have two answers. One is, yes, the simplest, less controversial answer would be to say true. Yeah, this also happens on a liquid obeying Newtonian dynamics. Everything's deterministic. So what happens afterwards is a consequence of what happened before. The problem is that decoding that from the structure can be extremely, extremely hard. If I gave you, I can give you, a still picture of this particle and tell you, well, solve Newton's equations in your head or whatever, and predict that over a period of time this region will be fast and region will be slow. It's very, very hard. People have been doing it for decades, trying to.
So should I learn from this that in these systems, it's the energetics of state space that I shouldn't be looking at? It's other properties that I'm more interested in. Because the energetics, as you say, are basically uniform.
So I'm going to say that structure is very unrevealing, and if what will happen dynamically is encoded in structure is extremely difficult to extract, and it's totally apparent in the trajectories. So you should rather look at trajectories, and these are highly nonlinear, highly strongly interacting, blah 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 systems. So the connection between structure and what happens dynamically is so complicated. This is a better approach. And then there is another discussion we could have about the fact that if it's a stochastic problem, the mapping between dynamics to statics is many to one. Yeah, like one uses many Monte Carlo techniques to try to get a given Boltzmann distribution, so to speak. So that mapping is many to one. So dynamics in the stochastic sense has something more than what controls the eventual steady state. And we can talk about that. So, and that becomes important.
So the sort of quantum analog here is just the Marlowe triplet for a single particle like that. I wouldn't think to see it unless I look at actually these time correlated events.
Yeah, something like that. Okay, so this trying to set the scene. And so dynamics and most I wanted to give you a complete, time, relevant example that's much studied nowadays. So for classical stochastic systems, also for classical deterministic systems, but stochastics is easier. For classical stochastic systems, there is a ready-made way to construct these statistical mechanics of trajectories. And it's based on dynamical large deviation. It has long history in physics and in maths and parallel and people rediscover things in parallel and so on, but it's existed and it has been hasn't been applied that much until recently within a physics, more physical context. And with that one can construct what I'm calling a thermodynamics of trajectories, this statistical mechanical analogy dealing with trajectories. Sometimes called the S-ensemble method, and I'll tell you a little bit about it first. And then, after that, I'll talk about the quantum analog. And I don't know when did I start? Are you keeping time?
Quarter past.
Yeah?
It was quarter past.
Quarter past. Okay, you tell me when to stop. Okay. So let's go back to this problem. And one of the things I'm going to say is that for open quantum systems, that's where I'm aiming. They are on the one hand, so they are different, but on the other, they are similar enough to classical stochastic problems that translating these ideas is relatively straightforward. So, that's again, the projection of the trajectory in this glassy liquid I was showing you before. Here, for simplicity, I'm showing some idealized lattice model, which happens to be a good model for glass. It doesn't really matter because I can show a trajectories in 1D, and so that's space and that's time, and these are spins that live on a lattice in 1D, and then one can draw a trajectory. Yeah? And what I want you to take from here is that in both problems, the configurations are trivial. In this lattice problem, the configuration is just like a non-interacting binary gas, but the way that these configurations follow each other in a trajectory is complex. And one can see here there is this emergence of reds and blues, large correlated dynamical regions. And in this problem, in the trajectory, you can see there is areas in space and time where lots of spins, flips occur, and then areas where they don't. Yeah. So now, if one looks at these systems and says, well, can I find a quantity that characterizes these fluctuations? That's what they are, that one is saying. And sure enough, there is a quantity, for example, the number of spin flips and how much the molecules have moved, which is different in these different regions. Let's call that activity. So that's an ordered parameter for a problem of this kind. It's how much something has moved over a period of time over a region of space. So it's natural to call it activity. But also notice that the key thing is that time integrated. It's an ordered parameter that looks over a period of time. This is a correct ordered parameter for a trajectory, where when we're looking at only at configurations, ordered parameters could be magnetizations or density, local densities or whatever. And clearly this distinguishes that behavior from that behavior. So that's a good ordered parameter. So once one has an ordered parameter, what you and by the way, if these trajectories look like this and like that, and that's the ordered parameter, and one looks at the distribution of the ordered parameter, what one sees is that there might be a Gaussian bulk to that distribution, the typical behavior and some Gaussian fluctuations around it. But in these kind of problems, they develop a very prominent tail, which happens to be exponential for reasons I can explain. But the key thing is a tail away from Gaussianity. So there are large deviations in this dynamical order parameter, in this time-integrated order parameter. So if one takes an ensemble of trajectories and calculates the distribution over this order parameter, there are large deviations. Yeah? And the large deviations are manifestations of those large fluctuations. If one had taken in these problems just a static order parameter, everything would be Gaussian. So it's really encoded in the time integral. So this is the emergence of large deviations. So longer times, at times which start to become long, tails develop, which are manifestations of fluctuations which are much more probable than Gaussian. So the large deviation aspect is, I'm showing here is a statement that there are fluctuations which are rare, but much less rare than if they were Gaussian. Yeah? So how does one proceed? It's very straightforward. So that probability I just showed you that has large deviations, when time is large, it develops what one would call a large deviation form. It's exponential in time times some function. It's really a function of k over t, but never mind. Times some function that controls the shape of that probability. Sometimes it is called a large deviation rate function. And the same information is contained in the cumulant, in the moment generating functions. That's the average of the exponential of the quantity times some variable I'm calling s. That's the moment generating function, and because this one has a large deviation form, this one also has a large deviation form. It's e to the t some other function, theta of s. So now we have the thermodynamic analogy we were, I was talking about. Because this looks like a partition sum, and this looks like the probability for an ordered parameter. So this is the ordered parameter. Think of magnetization or energy or number of particles, and this would be like its conjugate field. Think of inverse temperature or magnetic field or chemical potential. Yeah. So in that case, the function phi would be an entropy. It's telling us the log number of, in this case, trajectories with a certain value unobservable. So that's like an entropy. And if this is like a partition sum, the function theta is like a free energy. Yeah. And just like entropies and free energies, or whatever pair we choose, they are related by a Legendre transform. So each of them knows everything about the problem. And so if one finds the free energy or finds the entropy and so on, one can transform it to the other and knows everything about the problem. But the key thing is that because these are trajectories, their dimension is controlled by the spatial dimension of the system and by time. Yeah? And the novel thing here is that time is the large parameter. So time is like a volume. Yeah? So the large parameter is time, and that's what gives this large deviation form. So, and what happens is that if one goes to one of these problems, and it's when it becomes interesting, so I was saying, well, there's nothing interesting in the thermodynamics of these problems. If one does these quote-unquote thermodynamics of trajectories, for example, by calculating this free energy-like quantity, which is the generator of the cumulants. So it's a cumulant generating function, so its derivatives give the cumulants of the function of interest. What happens is that that function has a singularity at s equal to 0. Yeah? So remember that to calculate cumulants, one takes derivatives and then sets it to 0. So that function has a singularity which occurs in the large time limit and also the large spatial dimension limit. So one tends to that singular form. And the first derivative is the average of the quantity of interest, in this case the activity, the number of spin flips. Yeah? And because there is a singularity, that quantity, the order parameter, can have a jump. I'll come back to this later, but this is a first order phase transition in a physics language. But this is saying is that these systems are living. When one looks, nothing's happening thermodynamically. One looks at the statistics of trajectories, clearly one sees that there is underlying these phenomena a first order phase transition in those ensembles of trajectories. Yeah? Just by looking at the statistical properties in our appropriately chosen time integrated data. So, that's what I'm saying. So one can reveal in this way that there is a phase transition in ensembles of trajectories. That's why this dynamics is complex, not because there is a phase transition in the statics, there is a phase transition in trajectories. And what one sees here is the coexistence of active and inactive dynamical phases. The two phases that the transition is about is one phase where stuff moves, one phase where stuff doesn't move. One is here at conditions where there is sort of coexistence, one sees both. Yeah? Think of liquid vapor when you're sitting close to phase transition. Yeah? You have a liquid phase, you have a vapor phase. And if that's the case, say you're on the liquid side, you see bubbles of the vapor. That's also a large deviation phenomenon. And so these are large fluctuations of the other phase. So these are indeed bubbles, but they happen in space and in time. So these are bubbles of inactivity associated to this phase transition. So what happens is that if one can formulate, and it's very straightforward as I told you using large deviation theory, a statistical mechanics of trajectories, then one can bring to bear all we know from stat mech and thermodynamics into a dynamical problem. Yeah, and start thinking of these collective interesting dynamics in terms of phase transitions, phase coexistence, bubbles, you name it. So that's kind of my intro. It took most of my time, but so that's kind of the intro, which is everything classical. So the question is, can one apply these same ideas to open quantum systems? And the answer is yes, and that's what I'll tell you very quickly in what follows. So, and we think it was an open quantum problem that evolves in a Markovian way, so you shall think system, weakly coupled to bath traced out, description for the remaining system in terms of a Markovian evolution, in terms of some quantum master equation, a la Lindblad, and these ideas about stochastic open dynamics also deserve a lot to our late colleague and friend Slava Belapin from Nottingham, and many other people have developed this, and it's pretty standard nowadays. So the density matrix of the system evolves according to some Lindblad what's generated by that Lindblad-like operator like this. So I think it's something very, very simple, like a two-level system, laser-driven or resonance that's emitting into a zero temperature bath, so that it has a Hamiltonian with some Rabi frequency and operator that will make it tumble between these two levels, and then a jump operator that flips it with some rate gamma. So if one observes on the bath the emissions, that's the quantum jumps, one gets a classical trajectory, quantum jump trajectory, a classical trajectory of these observations of say the photons coming out in this simple example. And you guys are experts on these things, know much more than I do about it. But it's the kind of problem we're thinking about. So open quantum systems where one can observe classical trajectories of emissions of quantum jumps on the system due to the presence of the environment. And then the game is exactly the same as before, is to develop a statistical analysis of those trajectories, which is akin to StatMech. So then, once again, one can think of the number of jumps as a dynamical order parameter for a problem like this one. That makes sense. Lots of jumps is very active, lots of jumps is very inactive. Of course, it could be other order parameters, and I think I'll say something more later. The key thing is that something has to characterize the trajectory. It has to be time integrated. It has to depend on the whole trajectory. So once again, at large times, it has a large deviation form, and the moment generating function, this function set of S, the average of e to the minus sk, also has a large deviation form. As discussed before, these are like, we have our thermodynamic analogy once again. Yeah, large time is like volume. We have an order parameter, which is the count, what we're counting. There is a conjugate field, let's call it counting field, order parameter distribution, partition sum, entropy and free energy related by the Legendre transfer. Yeah. So then, once again, the name of the game is to calculate either this function or that function, and then we know everything about the quantum jump trajectories in terms as classified by this order parameter. And as usual in StatMech, one wants really to calculate the free energy. As I showed before, the analytic structure of the free energy tells us about phases and phase transitions. And that's the first information we want. Is there a single phase, or are there two phases? Can one think about the phase transition or not? Or the fluctuation behavior one sees. So now, calculating partition sums is tricky, and therefore free energies, but there is a slight advantage in this problem, which is otherwise in general pretty complicated, which is that this function theta of s, this free energy-like quantity we want, is the largest eigenvalue of a tilted or deformed operator related to the original dynamical operator. In this particular case, because we're counting jumps, if one has to deform it by multiplying this jump term by e to the minus s. And then the largest eigenvalue, which is 0 in this case because probability is conserved, is non-zero anymore as a function of s, yeah, but that's the function we want. I'm thinking, at a StatMech, that's because if this is a partition sum, this deformed operator is what one would call the transfer matrix of the partition sum. So basically the partition sum is this operator exponentiated times t and taken the trace. And that's the transfer matrix. And very often in StatMech, the problems one can solve because there is a transfer matrix and you reduce it to an eigenvalue problem, like the 2D Ising model, for example. Okay? So that's the simplification. The name of the game is you take dynamics, you deform it into this operator, you get the largest eigenvalue, you have the answer. The only thing to note is that this is a way of conditioning the problem. This might connect with the previous talk. Yeah? Because this is saying one is trying to look at conditioning the trajectories on a certain value of this observable, or rather it's of its conjugate field. So this operator will generate conditioned dynamics. And conditioned dynamics is not true dynamics, because true dynamics conserves probability. What conditioning does is select, filters out, I don't know what the right word is, certain trajectories, the trajectories that obey, that are weighted, if you want, by e to the minus sk, artificial. So this is a conditioning problem, this is not. Yeah? And therefore it's not real dynamics. Probability is not conserved. This is selecting, filtering out certain trajectories with a certain characteristic. So let's look at a couple of examples. So I cannot distinguish the large from the small of those two hands. Okay, this is 10 to 12. Okay, so it's something slightly less trivial than the two-level problem. Let's go to three-level problem. Still very, very trivial. Very small Hilbert space. Blah blah blah. We have two levels on resonance, 1 and 2 with different Rabi frequencies. Let's say one large, the frequencies differ, and one emits into this level 0. It's typical blinking problem. And it's known that if one looks at the quantum jump trajectories, there are periods of lots of emissions and periods of no emissions and periods of, it's a fact, it's kind of textbook stuff. It's blinking. And basic physics is that sometimes the system is here, but rarely it gets shelved into that state and doesn't emit, and then it takes a while to come back, and then goes here and there's the emission or emission, so on. Let's play this game with the technology I was just telling you about. It's It's very easy. One can take the generator has a Hamiltonian associated with those two lines and has one emission associated to that. One can write the W, the deformed WS, diagonalize, it's a 9 by 9 matrix, it's analytic, and that's theta S. And this is how it looks. Yeah? If the two-level problem was the gray curve, and that function is basically, both functions are smooth, but this one is really just boring. The black one is the one for this problem. What one sees is that close to s equal to 0 has a large bend from following the two-level behavior to becoming almost flat. And remember that the derivative of this function is the number of emissions as a function of this counting field S. So on that side, the number of emissions is large, but on this side, because this is very flat, the number of emissions is small. Yeah? And furthermore, that change, the second derivative, has a peak around the s equal to 0. A peak from a small value to another small value. Okay, this is a small system, so there can be no singularities. The matrix can carry no non-trivial singularities. But it has a structure of one phase and another phase and a change, not a singular change, but a crossover between the two. And sure enough, so what we have is we have an active phase where there are lots of emissions and an inactive phase where there are few emissions. And if I condition the trajectories to those values of S, on this side the trajectories are like this, lots of emissions all the time. On this side, there are very few emissions, so that's the active side, the inactive side. But actual dynamics takes place at s equal to 0. So actual dynamics is taking place close to the transition between these two phases. There is a large peak in the variance, and that's because when one mixes this with that, one gets this intermittent behavior. So two things. So there are two phases, active and inactive. They are at coexistence. So we have bubbles of one in the other, if you want. It's first order because the jump, if this was a discontinuous jump, there would be a gap. So it's first order. First order transitions are associated with interfaces. We have water boiling, the bubbles have a clear interface between the vapor and the liquid. And here we have sharp interfaces between the two behaviors. It's not, a gradual change from lots of emissions to no emissions. It's sharp. So what this is showing is that this allows you to have an interpretation of a problem we know about, but which is much more thermodynamics in terms of phases and the coexistence between those two phases. Okay? So now, and just to remind you, so here we have something that's just one, it's a smooth function here, one that one can imagine would have a singularity there. Yeah? And if I go back to the Legendre transform that relates this free energy-like function to the function that controls the probability, if the function is like this smooth, then the probability is unimodal, it's essentially a Gaussian. Yeah? But if the function has a singularity there, so there are two branches which cross, and that's the singularity, then the probability has two nodes, and one would say it's bimodal. But Maxwell construction in physical systems, probabilities have to be convex. And if one has something that's bimodal, that means that there can be interfaces that interpolate between the two. And what really happens is that the bimodality is convexed out by a flat portion. Remember the flat portion of the probabilities in those relativistic systems I showed you before. Those are evidences of phase transitions, in this case in trajectories. Okay? So this example is a smoothed out version of this phase transition because the system is small. So the phase transition is sums of trajectories, and that's related to the singular theta s. So one can go to more complicated problems. I will skip these, which are truly extended in space. For example, take an Ising model. That's an Ising model with a transverse field, with dissipation. That's decay of the spin. So that's the Ising model in a transverse field. That's a quantum. It's a quantum Hamiltonian, but each spin can get flipped down through dissipation interaction with a certain zero temperature path. One expects that there will be something interesting because already the stationary state has something interesting. The dynamics is highly intermittent depending on the regime one is in. Once again, if one plays this game, everything suggests that eventually in the large size limit, which I cannot attain here because it's a finite sizes, and there is one phase, there is another phase, and there is eventually singularity between the two. And I will come back to this. But one can apply this technology to more and more complicated problems. And the idea is that this should be revealing in problems where one doesn't know the answer to start from. So I want to emphasize the thermodynamics that make aspect of this. So I just showed you that there is this analogy. There are entropies, free energies, probability distributions of order parameters, partition sums. Everything looks the same. Transfer matrices, etc. Another aspect of StatMech is the following. In standard statistical mechanics, the partition sum for a finite system cannot have singularities because its transfer matrix will be a finite matrix. And if there is a phase transition, it can only occur in the large size limit. Well, what it can have is have singular points in the complex plane of its parameters. Those are called Lie-Yang zeros. So the partition sum can be zero at certain complex values of its magnetic field or its temperature or whatever. And then eventually in the large size limit, those singularities will accumulate on the real line and become true phase transition. That's Yang theory, it's like 60 years old. Well, here there is a version of dynamical Lie-Yang theory. Let me go very quickly. So at finite times, remember time is like size for us. At finite times, the partition sum is a polynomial. It has to be. You're counting something, that something can only take a certain number of values, cannot become infinite, the partition sum has to be a polynomial. So it's generating function, sorry, it's a polynomial. If it's a polynomial, it has complex zeros, those are the Lie-Yang zeros. And it so happens that because this is a dynamical generating function, so it's a generating function of the cumulants will be dominated by those zeros. Because the cumulants are obtained by the derivative of the logarithm. So if this has zeros, the logarithm has singularities, the derivatives become poles. Yeah? So there is a direct relationship, I won't go into too much detail, between cumulants as a function of time and these complex zeros. The complex zeros are these Lie-Yang zeros of Lie-Yang theory applied to this dynamical setting. The cumulants are dominated by those zeros, which means the following. That one can measure the cumulants directly as a function of time, and from the this is this prescription, measure the cumulants using normal dynamics, not the unphysical condition dynamics, extract the leading zero, and then see how it extrapolates at long times to see whether there is some singularity associated to it. And this is a clear prescription of how to extract the singularities, rather than calculating the very complicated, very, very large eigenvalue problem of a many-body system, just measure cumulants. And then, just to show that this works, this is again that classical problem that has these large deviations in the probability, that singularity in these generating functions. If one does that and measures cumulants and plots the complex zeros and takes time, sure enough, they point towards the fact that there will be a singularity at s equal to 0. In fact, this actually gets the finite size scaling pretty well as well. So this method works. And to go to the complex case, for the 3-level problem, well, there is no real singularity, it's just a crossover. Yeah? But in the 3-level problem, the change from active to inactive is smooth and becomes sharper the smaller this second frequency becomes. So you have the green, you might not see the red, and then the blue is sharper. And if one plays these games of where are the complex singularities, the complex singularities exist as a function of time and they move, but the ones that get closer to the origin, and that's the physically relevant region, are the ones of the sharper looking change. So in fact, how close they are to s equal to 0 and how far away they are from the real line are indications of how sharp this change is. You see that these are very far from s equal to 0 and very far from the real line, and that's a very smooth change. Well, that one is something that eventually could become a step. Okay? And the same for this Ising problem, and then in that problem we expect to see an actual singularity, and one can obtain it from this analysis. So this, just to say, one can apply the same ideas, these Lie-Yang ideas about singularities of partition sums to the dynamical setting. And the nice thing is that might give a way to actually measure these things directly. The other thing that we know from StatMech is the following, is that we choose which ensemble we work with. And that's what you learn. First thing you learn in thermodynamics, which variables do you control? You might fix temperature and volume, or get, what is it, Garrahan free energy, or you might want to go make a Legendre transform and control pressure and temperature, and might control number of particles, might control chemical potential. These are different ensembles. And ensembles are equivalent in the large size limit. So the question is whether there is something, in fact, there is a similar ensemble equivalence here. So you have a couple of minutes, I'll go very quickly. And this work that also involves Yuka and Madeleine most recently. So what I've been discussing up to now is ensembles where the total time of a trajectory is fixed. You observe for a total period of time. And then you calculate how many events occurred. So total time is fixed, the number of jumps fluctuates. So it's like controlling volume, yeah? And then when we put S and we bias by the number of jumps, I'm sorry, this is very small, but these are biasing the probabilities by e to the minus s, the number of jumps that you see in that trajectory there. The trajectories are all of the same length, the same quote-unquote volume. The number of events fluctuates, and then we control them through something that's akin to a chemical potential, this parameter S. But why don't we do this? We fix the number of jumps. We say, okay, all trajectories will have k number of jumps. Yeah, but if we fix jumps, we cannot fix how long, how long these trajectories will be. Some we fix 10 jumps, some trajectories will be short, some will be long. Yeah, all of them with 10 jumps. So the number of jumps is the same, but the time fluctuates. So the time is fluctuating. So now, k is like the number of particles. Rather than control the chemical potential, we fix the number of particles, and instead of fixing the volume, we put a pressure, which I'm calling x. So this is a different ensemble. We have a dynamics that generates trajectories, and we terminate the trajectories at a given time, or we have the same dynamic, generating trajectories, we terminate them after a fixed number of events. And S and X condition these trajectories in two different ways. Now the question is, in the large size limit, when these trajectories are long, are they equivalent or not? So, the first one is a continuous Markov process, that's what we've been discussing. This one is in effect a discrete Markov process, because each of these blocks is like applying a Markov matrix, yeah, which might depend on time, or the number of jumps, but it's applying a Markov matrix, okay? And just like there is a partition sum and a deformed operator, there is a partition sum here with its largest eigenvalue of some other deformed operator. I can prove it easily, but I won't. I just say that at the level of this, there is what one could call ensemble correspondence. The free energy like function that controls this ensemble is directly related to the free energy function that controls this ensemble. So the statistics here of the jumps is directly connected to the statistics of the total time. And that's called correspondence, a weak form of equivalence. If one knows one can convert to the other, and the fact is that these two operators, the deformed operator and that deformed operator, share an eigenvalue, share the leading eigen state or eigenmatrix. I can discuss that. It's very easy to prove. Now, the thing I will say in 1 minute, and and when I say I mean Yuka can answer questions, is that one can prove something stronger, actual equivalence. And that's by a neat connection between open dynamics and matrix product states. So just like this one was continuous Markov dynamics and this one the discrete Markov dynamics, the whole ensemble, that is all possible trajectories under probabilities, can be encoded in a matrix product state. It happens to be a continuous matrix product state, the kind developed by Stratis, Dirac, and others. Which is basically saying, you can label all possible trajectories, and the probability of that trajectory is the initial wave function and the application of the quantum jumps with some waiting time. I'm sorry that this hasn't come across too well. So the quantum jump and some waiting time, until the nth quantum jump, and then some extra waiting time until the final point of the trajectory where no jumps occurred, summed over all possible number of jumps, and that forms a continuous matrix. So there's a big wave function, and this is very elegant, right? There is a big wave function that contains the whole ensemble, all possible trajectories with all their probabilities. Yeah? And this is a quantum wave function. It's not yet stipulated what measurement has been made. Yeah? So one can transform to another basis. So instead of counting photons, one could do homodyne. Yeah? So it's just applying some transformation to this wave function. So this knows more than just the trajectories I was telling you about. It's the system and the output, okay? In the other ensemble where the number of jumps is fixed, there is also a matrix product description, and this is a standard matrix product, because we don't have this variable number of operators we put. If we we have k jumps, we apply k operators. If we have n jumps, we apply n of these operators. And each operator is the jump and the waiting time. The jump and the waiting time, after n of those, the trajectory is terminated. It's a normal matrix product state. So once again, the trajectory and its probability, which is coming from the initial state and applying n of those matrices to that initial state. It's a standard matrix product state. And one can, that's what the dynamics produces, and one can define the condition well. And then there is ensemble equivalent. This is the last result, and in some generic sense, we can discuss it later. When the number of jumps is very large, the two ensembles are equivalent. That is, the overlap between the wave function that describes one ensemble and the other one that describes the matrix product state that describes the other ensemble, with some appropriate projection that just makes that is stating that one is comparing like with like. Yeah? In that limit, there is no distinction between those two wave functions. It takes the log and divides by k, so the distinction is sub-extensive in the large parameter. And that's a quantum version of the usual condition that one uses to compare two probabilities in the large system size in the classical sense. So then these two ensembles are not just correspondent in the sense that the free energy functions are related. The actual probabilities of the trajectories in the large size limit are the same. The two ensembles are the same. In the same way that we say, for example, that the fixed pressure ensemble and the fixed volume ensemble in statistical mechanics in the large size limit are the same. They describe the same physical properties. So, well, that's all I wanted to say. I don't know how, sorry it took so long. I just wanted to emphasize, where this was coming from. Second, that there was this natural statistical mechanics setup for dynamics, and the things like that follow. Possibility of observing these singularities directly through cumulants, and properties about ensemble equivalence. And then there are lots of interesting connections, how to make this condition prolonged into non-condition problems that relates to the things we heard about before, and then what we think are the applications to complex non-equilibrium quantum systems. And I stop there.
Okay, time for several questions.
It's a stupid question, but I did not really understand what is the physical phenomenon with this phase transition in the quantum case, for example, is this free level system.
Oh, yeah. So I didn't say that much. We have two examples: this one and the three-level system, the one I was showing there. All I'm saying here is that whenever you see intermittency in the emission, you can think of this as being close to a phase transition. So you get that intermittency in the emission, like these are true many-body problems, so there is space there as well. So this is emitting in space where you've emitted, and that's in time. So these are, if you want, photon emission trajectories, which record where the emission came from. When there is intermittency, if one thinks of the problem in this way, when there is intermittency in these emission trajectories, you can immediately think of a first-order transition. That there is, there are trajectories which emit very little, there are trajectories which emit a lot, and the system is close to phase coexistence. So it's a connection between intermittency in the dynamics and the existence of these competing phases.
So this is just the light and no light is the phase transition.
Well, it's a bit more because there is space here, and there's nothing that's telling you that the emissions have to be correlated. The emissions are clearly correlated in time. Yeah? You don't emit, or you emit, you don't emit, you emit. But they're also correlated in space. These are like these space-time bubbles I was talking about before.
This is already about the spins in the lattice.
Yeah. So this is the direction of the lattice in this one example of this quantum problem, and this is where there was a quantum jump in time and in space. Emission of a photon from a given lattice. So whenever one sees intermittency, there are these two competing phases. And then one expects things. They, oh, yeah, sure enough, there has to be an interface. And sure enough, there is an interface. Because if these are two phases like liquid and water, vapor and liquid water, I'm giving that example. The reason that there is that, the distinction between this and that is not something very rugged and smooth and difficult to discern, is because these are two phases at first order coexistence. So it brings in that way of thinking. Yeah? So.
I have a follow-up question on that.
Yeah.
So for the blinking
Yeah.
example, so I can see a time dimension, but what's the space dimension here?
Well, no. Here there is a single system, so this one point.
Exactly.
This is taken from some review, the plenty of.
But is there an analogous parameter that is hidden in there that is your space parameter? That's because the whole point is that you have.
Okay.
In
This is a single body, if you want, a few body problem. Yeah. So that's why this has to be smooth. There's no way to make this sharp
Oh right.
because
okay,
there is a
yeah.
single body. It's like saying, you cannot have a sharp translation in few body. But this is showing that already at the level of few body, there is this structure emerging. So what happens, and we have, I have slides even on this. One can start coupling, these subunits, and then you get this also spatially collective effect, and you can make this sharp. The Ising model is a little example of that kind.
Just on your question of the equivalence ensembles.
Yeah.
In classical statistical mechanics, well, you can have inequivalence of ensembles. Actually, the free Bose gas is one where the grand canonical and the canonical don't agree.
Yeah.
That's an example of a second order phase transition. I was just
So,
wondering, is there analog here?
True. I guess that this will happen here, and people think about that as well. It's very often related to long-range correlations and things ceasing to be extensive. But certainly it's true. Ensembles are equivalent except at phase transitions. That's one thing. Yeah? And then there is inequivalence of ensembles if you have non-extensivity, because you might have long-range correlations and so on. So those things should happen here. I don't think anything's different. Yeah? In time, all the examples I've been discussing, that's encoded in the existence of this large deviation limit. Yeah,
Yes.
There is an extensivity implied here. They're saying, well, I don't know how explicitly we say it, but we say, assuming that this large deviation limit has this form, then these things follow. Of course, and I'm not a super expert, but there are other large deviation forms where the powers that go here are not one.
That's right.
Yeah, and all these things have to be revised in that case. Or, in other words, all this applies to systems, which is majority of the physical systems where the correlation times are finite, or they become infinity in a way that one understands with system size as one approaches. Like one studies usual phase transitions is by approaching the phase transition point, essentially never at the actual phase transition, as limits of how the system becoming infinite and so on. And the same, everything applies here. So all the things you're asking about, there will be a setting, dynamical setting where they appear.
Just one further question, a bit more fanciful. If you were doing this in multi-input output setting, I'm thinking of things like Henry-Brown-Twiss experiment, or things where you've got interference.
Okay.
Would you expect, well, say with more than one input field, would you expect to see things like photon bunching and anti-bunching as being a type of phase transition between?
Okay, you will need to translate for me slowly. So you're saying...
I said it's very fanciful, so I haven't really done the translation myself.
I mean, I've learned all this input-output from Madeleine, so I'm almost about to ask him exactly to translate the question for me. But you're saying if you have more than one input, that means that you're interacting with more than one environment, quote unquote, correct?
Yeah.
So...
No, two input fields.
Well, which is you have two jump operators. That's two jump operators. Yeah, here there were many. Okay. So here there were many. Each of these pins had a different jump operator. So if you want, there was an input field for each of those.
It would seem that each spin is coupled to its own channel, and you can measure in that channel.
And you could count, yeah? The counting I was talking about could be a vector. Yeah, you could be counting simultaneously the number of jumps due to channel 1, channel 2, channel 3, channel 4. And then and in a sense, this is what this is. Because these trajectories are the emissions of each spin. So these are the jumps. So now, can you restate your question, please?
I'm really thinking of the statistics of the output, properties of bunching and anti-bunching, whether this corresponds to something you can see, you can adjust with your S parameter.
Well, yeah, sure. Here's a very, very simple example. So once it's bunched, this is clearly bunched. Yeah? And it's bunched because the susceptibility is large. So the Q parameter will be larger than 0. Yeah? And this susceptibility is large because you're mixing these two different phases. That's the bunching. If you go way to the inactive side, there is nothing. This is, if you want, Poissonian because it's essentially empty. Yeah? And if you go to this side, you notice that the Gaussian the variance is going to 0, or going to a small value. In these units, well, one has to normalize by this. Well, what happens is that on this side you're anti-bunched, because the two-level system, because of usual quantumness, is slightly depending on parameters, is anti-bunched. So you're already seeing it at the level of this example. Typical dynamics is bunched. Yeah? Inactive trajectories are Poissonian because they are basically empty.
Yeah.
But active trajectories typical dynamics is bunched. Inactive trajectories are Poissonian, and active trajectories are anti-bunched. And it's already contained here. So this is saying that the ensemble of trajectories of this very simple system, has an anti-bunched phase and a Poissonian phase, and the bunching comes from mixing them, from saying, chunks of each.
Jake?
So I have to say one thing I never really got, that might be on my own failure, is why I have to analyze this whole story in an open quantum systems language. In other words, in the glass story, there's some thermalizations going on and the like, but it's conceivable that I could write down the dynamical story with a completely closed system.
And
so here, I do not see a way to develop this sort of set of ensembles if I don't have any jump operators.
That's a good question.
So what am I missing?
And I'll give you an answer related to this slide. Okay, so it's easy to go from classical, and as you say, you have a classical many-body system, and in classical dynamics, it's always easier to look at stochastic. Because when it is deterministic, things are like stochastic because there is lots of chaos, but it's very difficult to prove. That's the usual story. So one looks at stochastic, but it's true. The liquids I was showing you, they could be in contact with a thermal bath, and you're doing Monte Carlo as a dynamics, or you could be doing molecular dynamics with Newton's equations of motion. It's the same. And the object you count is a time integral. Now, in classical systems, you can measure whatever you want without perturbing the system, right? So you just look, and you know it. So in that sense, there is no big difference. Going into quantum, it's easier to make the step first into open quantum systems because you have this output. And you can look at the output without perturbing the system, so to speak. It's been perturbed already, and those are the quantum jumps. In the closed case, you can do it. I don't know what this has information. This is an example. This is the quantumizing chain, a closed system. And what you might think of observing is the time integral of an operator. And they do the statistics of that time integral. Yeah? So you take an operator, you take the time integral, and that's your order parameter. Now what happens? Two things happen. First of all, in the open case, the time, the distribution of, say, the jumps is a probability. In the quantum case, you are not guaranteed that this quantity is distributed as a probability. It's a quasi-probability, a Wigner function, whatever you want to call it. So that's the first thing. So all the properties of convexity that probabilities carry, and the Legendre transforms and so on, are lost. But nevertheless, a fair quantum question is, what are the moments or the cumulants of this observable? Yeah, this is a Heisenberg operator, yeah, and it has cumulants. And if it has cumulants, you can define a cumulant generating function. And you can think of that cumulant generating function large time limit and think about its quote-unquote large deviation. It has something that's akin to a large deviation form. And I don't know what were the mathematics of this. It's all tidied up or not, but one can do it more or less heuristically. Yeah. And sure enough, this function reveals singularities as a function of that counting field, and one can think about the physics of those singularities. So one can carry on this program, and we are doing it. And there are analogies and there are differences. Yeah.
Related to this very moment, this very problem, what would happen if you add a tilted field and you break the exact solvability of one?
Are you saying what happens if you put an imaginary field?
No, transfers. This is tilted. This is transfers,
Oh,
but
oh,
this is nearest neighbor and it's exactly so.
Oh, I don't have a slide for that. We've looked.
So if you add another.
Yeah. We've looked at the transverse and longitudinal. That's a question field. So the problem with transverse and longitudinal fields, is that your question?
My question is like, what happens if you make this non-integral?
That's what we looked at that.
Okay.
So if you put a longitudinal, this is a transverse field. If you put a longitudinal field, you cannot make it integrable. It's not integrable anymore. That's your question. With both fields.
Yeah.
Okay, we looked at that. And something interesting happens in that case because this cumulant generating function, or this moment generating function, is related to a non-Hermitian operator by construction. In that case, in the case you're talking about, this is a non-Hermitian operator that has PT symmetry, parity. Okay, so it has a PT symmetry and has a regime of broken PT symmetry and a regime of unbroken PT symmetry. And there is a set of transitions of this kind associated with the breaking or non-breaking of that symmetry. Because depending on whether you break it or not break it, you have complex or real eigenvalues. And if you have real eigenvalues, like you've done nothing, this is a unitary, there are no moments. So if one can, again, through this technique, see a region of quote-unquote trajectory space, I don't even know how to call it in a closed system, where there are the fluctuations are highly suppressed, the cumulants basically vanish, and another regime where they don't vanish, where the fluctuations are standard, one would say, and that's related to the PT symmetry of this operator, in the case you're talking about. So yeah, we've looked at it.
I guess what I'm asking more broadly is whether this perspective can shed a different light into understanding the role of integrability versus not in many-body isolated.
Yeah, that's a good question. I don't know. I don't know what. So to be honest, we looked at this because it's solvable. It's even solvable with this imaginary perturbation. Yeah. So that was the first study we did, and the second one, the one that's non-integral because it has this PT symmetry. And yeah, that's an interesting question. I don't have an answer.
Okay, if there's no further questions, let's thank Juan and also try from